Okay. All right, so the first thing that we want to look at is we need to solve the capacitance total. So capacitance total is equal to capacitor 1 in parallel with capacitor 4 in parallel with capacitor 2 added to capacitor 3. Because they're backwards from the resistor rules. That gives us a total of 707.224 nanofarads. Okay, once we have that, we can solve for our I total. Any questions about how we got that? Okay. 440, okay. So, we take C2 and C3, we add those guys together, so what is that value? 12.4 micro in parallel with 6.8 micro and in parallel with, 1. Okay. So we plug those into our calculator. We get 1 micro parallel with 2 micro parallel with 12.4 micro. Take the inverse of that. You get 632. Is that close to what you got? What'd you guys get? Same? I fat fingered it. It's the 707. Okay, so we get the 707. Okay. After that, do what? No. Okay. So to solve for the I total, we need the voltage total divided by the reactance total. So this is one of the places where you have to solve for your total reactance. Okay? The reactance total is 1 over 2 pi times the 760 hertz times the total, which is the 707.224 nano. And that comes out to be 296.106 ohms at negative 90. You get that value, Simon? That is the reactance total for all of our capacitance. Okay? Now that we have that value, we can plug it in over here. We have 13 volts at 0 divided by the 296.106 at negative 90. And that gives us a total of 43.903 milliamps. Okay? Now that we have that, we can come back across and we can solve for the voltages. We can just use voltage divider at this point. Okay? We don't have to go through and solve with current because all we have is capacitance. The phase angles are the same, so we can do this. So when we solve for that, the voltage of C1, and since we can use the capacitance to solve it, like when we first were playing around with capacitors, we're going to take the voltage total, and then our ratio is going to be the capacitance total over the capacitance of 1. Because it's a parallel relationship when we get into the series. So we have the 13 volts multiplied by our total, which is 707.224 nano, divided by the 1.2 micro, and that gives us the 7.662 volts. Voltage for capacitor 4 we'll do the same thing, except for we'll swap out capacitor 4's value. So we get 13 times 707.224 nano divided by the 1 micro, divided by the 2 micro. That gives us the 4.597 volts. Huh? This is using voltage divider. Because when we're using, because of the values that we're using, they are treated as in parallel. So we have to flip that internal ratio. So in this case, our voltage divider uses the parallel ratio, which is the total over the individual versus the individual over the total. That's the only reason why.
Okay, the reason I think it does that, just going around one way, is because it's the inverse, so the 1 over the 1 thing, because you multiply the regular total times the inverse, which flips the other one since it's a 1.
Right, that's the part, yeah, that's...
So that's why it doesn't make sense logically to have the total on the top to get a fraction.
Yep.
Because, whoa, I'm learning math.
Yes. Okay, Simon? That's still within the tolerance. Reactances? Yeah, yeah. No, you're good. As long as you're within your 5% tolerance. Okay? So now that we have these two values, they're in phase, so we can directly subtract from the 13. So the capacitor 2 and 3, their two voltages are going to be the same, and it's going to be whatever is left over. So we have 13 minus the 7.662 minus the 4.597.
It's the Russians.
Okay. Also, this is what we should expect as well. Okay, 0.7 volts, considering how much capacitance we have. In this branch, we have a total of 12.4 microfarads versus 2 and 1.2 microfarads. That's going to have very, 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 very small amount of the voltage compared to everything else. Higher capacitance is lower voltage. Because as you have a higher capacitance, you also have lower reactance. So it's going to take a smaller portion of it. So now that we find the voltages, we need to find the reactance value of capacitor 2. Because we know the current through C1, C4, it's going to be the total current. We know that these two guys are going to split up this total current. So all we have to do is find out how much current is going through C2. The rest of it has to go through C3. The voltage of C4? So this guy right here. So we're using voltage divider, but we have to swap this internal ratio because the capacitance values we treat as in parallel in a series circuit. And so because of that, we have to flip the total and the one we're looking for. Because normally we would do the one we're looking for over the total. If we had solved these guys down and we're using reactance to solve for this, we would put it back to normal because resistance is resistance in the circuit. This is only because we're dealing with a capacitance value. Okay, so x of C2 is 1 over 2 pi times the 760 hertz times the capacitance, which is 6.8 microfarads. And that gives us 30.796 volts. or sorry, ohms, not volts, ohms. We then have our voltage and our resistance, so we can solve for the current of that branch. That gives us 24.062 milliamps at a positive 90. Then, because, like I said, these guys are all in phase, so we can directly add and subtract, we started with the 43.9 milliamps. We take away the 24.6062, and what we're left with is the current through C2. So, 43.903 milli minus the 24.062 milli, and we're left with 19.841 milliamps. And again, you could go through this entire process and solve for every single one of the X of C's. Go through all those. When we get to this point for the RC circuits, we will want to take it out through every current, every resistance, every reactance, because we will not be able to take these shortcuts, basically. They will be out of phase. Okay, so to compare, when we draw this guy up, we want to put in all the voltages. So scroll up just a hair so I can read them. The voltage of capacitor 1, when we would look at it on our chart, would look like this, or on our oscilloscope. 7.662 volts. Is that correct or not? Huh? It would be in RMS, but we can just say it's peak for this example. We're not going to go through all those conversions. Okay? So our total voltage is going to look like this. So this is V total, or V gen. The voltage coming. V gen is the voltage of your generator.
That's what I said.
Okay. The next one we're going to have is this. So this is voltage of capacitor 1. This is voltage of capacitor 4, and it comes in at 4.597 volts. Yep, they're all in phase. This is going to be V capacitor 3 and V capacitor 2, and it's 0.741 volts. So if this was our lab and we were drawing these values, we would draw it in like this. We would also need to indicate our frequency is 760 hertz. And then we have everything labeled with what their value is and what their names are.
So it does 761 of those every time.
Yes.
So that's what my
So just a second, Carson. You either need volts per division. You don't have to have them on there. It helps because you're going to have the pictures of your graphs behind there. But those will be shown down here in the bottom of your screen.
So that's what my lab book should be looking like, right?
Yes. For waveforms, yes. Okay, Simon? Yes. Yep, your given voltage will be the max, with a couple of exceptions that we'll talk about later on down the road. We have a couple of cool phenomenons in here. So this is how we would want to display it. It becomes very important. I mean, when we're dealing with resistors and capacitors, everything's going to be nice in phase. It's going to be really easy, really pretty to do. Okay. This next portion where we start getting into resistors with these circuits, when we start solving them, these things are going to be shifting around, so it's going to become more and more important to start graphing these things accurately. We can't just throw something down. We got to make sure that if somebody was to come back behind us everything's going to match up, and we get specifically our phase angles, because our phase angles, we can tell a lot of a circuit just based on its phase angle.
So just the process is, if a resistor's in there, it'll shift the phase of every part that it affects, or just the nearest one?
Everything.
So with the parallel ones, it'll only affect that branch of the parallel.
It'll affect everything. It'll affect everything.
So say we attach the rheostat into the system, and we fully turn, that we see everything start going out of phase?
Yes. You would start to see things switch. They'd come out of phase, and eventually they'd come back in phase again, because your resistors is going to completely overpower it. It will. But there is a method to the madness. That's why we're teaching you guys these. Okay, any questions about this series parallel circuit? Again, just take it step by step, just as if you were doing a resistor circuit. Okay? Convert everything to reactance, then it is just a resistive circuit. Okay? It's the exact same steps that we did for solving any of the other previous equations. Now, we're not going to get into loaded voltage dividers with AC and capacitors. We're not. That would be a lot. Could be a bonus question, but
I can barely do them the first time.
see, that just makes me want to throw it in.
Bro, I can barely do them the first time, man. He's part on our downfall.
Let's see. Okay, crap. I'll be right back.
They also all have chlamydia. Fun fact. Look it up. Look it up. It's basically part of their DNA.
Okay.
Their DNA.
Any questions about the series parallel capacitors? Again, it's just going to take more practice to go through them.
I can just go back into this room during that conversation and just maintain composure like that.
It's easy. I was not paying attention to most of it. Okay. Moving forward, we've been talking about the different aspects of the waveform. We have our peak, which is the maximum or minimum values. Peak to peak is the distance between the two peaks, your positive and negative. The instantaneous voltage. This is any of these voltages along this curve. We could solve for at any point based on our time or the phase angle, essentially, what the voltage is going to be. RMS, like we've talked about, is root mean squared. It's the effective average of the voltage of a curve. Okay, going into calculus, you'll figure out how that's created. It's the DC equivalent of the waveform. When we're talking about power, what is our resistance? Power across the resistor. What do we call it? Heat, true power, real power, things like that. What do we call the power across reactive components? Not imaginary. It's stored power or reactive power. It's not power that's actually used. And then the combination of the two, parent, they do not give off heat. If they give off heat, they blow up. Okay, one new term that we're going to introduce you guys to. Yes. Okay. Is impedance. We give it the label as Z. Impedance is the combination of real and imaginary, real and reactive values. Okay? So it's real and imaginary. Or reactive. we're going to look at it in terms of the real value plus or minus the Jx value. So whatever the reactance is, positive or negative, depending if it's capacitive or inductive. We also will see it as this. At some magnitude z at an angle, which is what we've been solving for these times in lab. Anytime we've been having here with our XCT, that is the same as our impedance in those circuits because there is no resistive properties to it.
So, impedance is the combination of imaginary.
Yes. Yep. Okay. The phase angle that we have, or our phase shift, so if we have a waveform, we're going to have a value that looks like this. We're going to have a value that looks like this. The difference between these 2 points, so basically we want to compare, when it's doing the same thing. When it's going positive and it crosses the x-axis to when the other wave is going positive and crossing the x-axis, that's where we want to mark our time. In this, we refer to this as delta t, which is just the change in time from those 2 locations. This can be given as either a time or an angle. How do we determine that angle? With the triangles. Okay, but if we're just looking at it on a graph like on our waveform like this, how would we figure out what that phase angle is? For what? Cursors, yeah, they would give us the cursor, so we would give us this time. So let's say this one came in at 0 microseconds. This guy came in at 16 microseconds. And the last part we need is the total period of one waveform. Okay? So if this whole waveform is 160 microseconds, we can find out what the phase shift is. How would we do that? Okay. So 360 degrees, full waveform, positive iteration and negative iteration, is equal to how much? 160 microseconds. So essentially the period is equal to x number of degrees divided by delta t. P is period. So in just a formula, that's what we're looking for. We have 360 degrees is equal to our period, or over our period, is equal to some number of degrees divided by the change in time that we have. What are we leading or lagging? So in this case, we would have 360 degrees divided by 160 microseconds. We want to solve for x number of degrees, and our delta t, I said, was 16. Now we just solve for that value. Yep, so we take 360 times 16. The phase angle is 36 degrees. So when we'd be looking at this, writing it down, if this was our generator spitting out some voltage, this would be the value of either the resistor or the capacitor, depending on which one we're looking at, probably the resistor, or probably the capacitor because it's lagging. So what this would be is this would be some value at negative 36 degrees. And the reason it's negative is because we want to look, is something occurring first in time or occurring second in time? Later in time. Okay? So this green signal is it occurring before or after our reference signal? After. So it's going to have a negative phase angle. So go in this direction is negative phase angle. Go in this direction is positive phase angle. So this is when we solve for these guys. When we get these values, this is what we're going to start figuring out. So we can go back and forth between either an oscilloscope drawing or a mathematical function with the angles. And it won't matter what the scale is. If we change this up a tick or whatever, this moves it up to, this is going to be 0.16, and then the other one would be 16. It's still going to follow the same trend. We still have the same distance between them. We've just changed our scale. Or if we increase the frequency, things like that. Mm-hmm. Yep. And so it's going to be from the same spots, because this waveform could be clear down here. So we want to go from when it crosses the x-axis as it's going positive. That's where I like to take my measurements. You can take it from here when it's going down and crosses the x-axis from the positive. It doesn't matter as long as you're doing the same thing to both sides. I just like going from where it crosses the positive, when it's going positive and it crosses the x-axis. Okay, again, the green one is coming after the red one. So the green one is doing what? Is it leading or lagging our reference? Lagging because it's coming later in time. So that's the difference between leading and lagging. And that's important to understand which one is happening first. Let's see.
How do we get the P value again?
P is period. So it's going to be the full, how much time does it take one cycle to complete? Which we could also find by our frequency. If we knew that, we could find that and take the reciprocal of that. A lot of the scopes that we have will give us the period as well of the waveforms. It'll display that up on your screen. So you can have your screen display just about all the information you could want to know about this waveform in one fell swoop. Analog. It would still trace it, but then you would have to count all the divisions and set it up yourself. A lot more accurate to use the digital ones nowadays. Okay. So earlier I was talking about we have the reciprocals of our values that we have different names. So resistance, what was the reciprocal of resistance? Not reactance.
The one that sounds like it's like allowance.
Conductance. Okay. Resistance we designate with what variable? Ohms, and it's also R. Okay, conductance is, you guys remember? G. It's because we have way too many things to go with C. So we got to split them apart a little bit. So these are the reciprocals. So R is equal to 1 over G. 1 over G is the same as R. So like when we were finding parallel circuits, we would take the reciprocal of the resistance, add the conductance values together, and then take that total value and convert it back into a resistance. We do the same thing, we just have a separate name for them for reactive components. So we have reactance, that is an X. The reciprocal of that is susceptance. Yes. It's the susceptibility. It's how easily is the ability or the device able to charge or discharge or build up a magnetic field. How susceptible is it? And then we have impedance, which is the combination of resistance and reactance. And its opposite, reciprocal, whatever you will, is called admittance. And the reason why we want these is because when we start getting into series parallel circuits with capacitors, inductors, and resistors, we're going to start flipping these values back and forth. We're going to take the reciprocals of them. We can use product over the sum, any of the same rules we use. But as we do it, we have to remember what are our units, because we're going to be taking reciprocals of a lot of different things. Okay? What are these guys all measured in? Resistance, reactance, and impedance. Ohms. What is conductance measured in? The conductance measured in. Not ohms. Siemens. Okay? Yeah. Everything here, so over here, all these guys are measured in Siemens. These ones are all measured in resistance. Because A we have is amperage. Huh? Capital S. Tiny s is seconds. Okay. We're going to go back and forth between these all the time. This way we can talk about what value we're looking at. Because this way if we're writing it down and we want to share that information, we can say, okay, it's either susceptance or it's a conductance, meaning it's either real or imaginary. We just taken the reciprocal of it. Correct. Yes. Yep. Another big thing we need to remember is how everything is referenced. Our horizontal is considered our resistance. It's 0 degrees. It's also 0 J. No imaginary components to it whatsoever. Pure capacitance sits down here to the bottom. It's negative 90, and it's a negative J value. Inductance sits at the top, positive 90 degrees, and it's a positive J value.
Wait, is it just L or is it XL?
XL. So in terms of all the resistances that we can have, these are both reactances, but one's going to be positive, one's going to be negative. Whereas real resistance, it's always positive because we can't have a negative real resistance. Imaginaries, we can do whatever the hell we want because they're imaginary. I mean, really, we can do anything we want to. It doesn't matter. Okay. So keeping these in mind, this is how we're going to build and study our circuits. So very basic circuit to start with. Will be a resistor and a capacitor. We have 12 volts peak. We've got 1 kilohertz. R1 is 15 ohms. Capacitor 1 is 10 microfarads. Yes. Yep, because we need to find total impedances on this guy. Okay? So like you're saying, we need to solve for our x of C1. Using the same formula, 1 over 2 pi times our frequency, which is 1K, and the capacitance is 10 micro. Yep. Okay, what's the angle of our resistor? 0. Because it does not care about the frequency. Phase angles, it will just follow.
So does that mean that the capacitor is going to be lagging behind the resistor?
It will be.
Nah, I learned something.
Okay? So what we need to do is we need to be able to solve for all of the regular variables. We need to solve for our current so we can solve for the voltages. Well, now these guys are out of phase. So now we have to do a little bit more in-depth math. We can't use any of our tricks. So we need to find the impedance total of the circuit. Okay? They are in series. What can we do? We're going to add them together. So we have, 15 plus j of 0, okay? Because again, we have no imaginary component to this resistor. We add that to, so with this guy, we have to add the value. It's in polar. We have to convert that value into rectangular. But because it's at 90 degrees, what can we do with this? Well, yeah, we would use the sine and cosine to change it, but what's the shortcut that we can do when we're at plus and minus 90? How much real, how much imaginary is there? Looking at this again, if it's sitting down here at this negative 90, huh? At the end it will be, yes. Okay? For our capacitor, we have 15.91 at negative 90. So we're sitting right here on this line. How much real part do we have? 0. Okay? How much imaginary do we have? Okay? Negative 15.915. So minus j 15.915. When they're at 0, when they're at plus or minus 90, we're going to have nothing in the other component for what it is. If it's 0, it's all resistance. If it's negative 90, it's negative j, no real part. And if it's positive 90, it will be all inductance, which would be a positive, a plus j. So now we have this. Now we can combine it together like we were doing 2 weeks ago, adding like values together. Combine the reals, combine the imaginaries. So our impedance total ends up being 15 minus j 15.915. That's all good and great. We need to solve for current. So if we're going to do division, what does this have to be in? Polar. So we have to take this guy and convert to polar. This is where we start getting back into the trig. Okay? Okay? Coming back to our graph, if we were to plot this point, we would go 5, 10, 15, 5, 10, 15. We'll set up our chart. We go to positive 15, and then we go to just a little bit past this one. So we've got 15, negative 15.915. Okay, that's our point. We want to turn it into polar. So we need to solve for this value and this angle. If we finish this off, we end up with our triangle. So 15 real, 915. This becomes our Z. We need to put it in polar so we can solve for our current, so we can solve for the voltages of this guy. We need to find both. So Pythagorean's theorem will give us this value. So we take r squared plus x of c squared, the square root. That will give us the magnitude of this line. Sure. What happens when you square a negative? Becomes a positive. So yes. Okay? Now, how do we solve for this angle? Okay? Which ones do we have given to us? We have r and x. So according to this angle, what do we have? Tangent. Okay? Yeah, we take the arctangent. And it's negative. Because we have to make sure we're using this value. If it's positive 15, that means we would be up there. So those angles are, yes, the negatives are important, but when we're squaring them, doesn't matter. We can kind of let that one slide. So we plug this value in. Now we're going to get this angle, our impedance at some angle. Because then we can divide voltage into this to be able to get our current. So it's all about what answer am I needing? Do I have to multiply, divide, add, or subtract, which is going to dictate which one of these we need it in. So this is going from rectangular to polar. There's going to be times where we're going to go back from polar back to rectangular. So we're going to use these a lot, but just remember, going from rectangular to polar, we take the real value squared plus the reactance value squared, add them together, take the square root of that, that gives us our magnitude. We take the inverse tangent of the negative xc divided by r. That will give us our angle. So what does the angle come out to be? Exactly. That's one of our other key indicators. If these guys are close, we should start seeing it approach 45 degrees. And we'll know if it's either getting smaller than 45 degrees or larger than 45 degrees based on which is bigger. The capacitance is bigger, or the capacitive reactance, so it's going to be on heading towards the negative 90. So our impedance total is, what did we get for this value up here for our Z? 21.87. Solving for theta was using tangent. This one was just using Pythagorean's theorem. Okay, so this is where we're going to pick up tomorrow. So right here we have our total impedance for this circuit now. We have 21.87 ohms, and it's running at a negative 46 degrees. Once we get through that, we'll solve for our current, we'll solve for the voltage, and then we'll come back and plot them so you guys can see what they look like. Okay, that's all we got for today.